Ashish? Okay, okay. Sorry to interrupt. Go on, Ankit.
Yeah, no worries. Yeah, so good evening, all of you. I guess it's evening, and today we will have a talk, rather on ground station as well as radio astronomy part. Um, for us as since we are amateurs in this particular field, so I will be much more stressing on the amateur part rather than the more professional part of it, which will rather be not much useful to us. So first of all, I will start with ground station because this is the basic of both radio astronomy as well as satellite tracking and other ground stations. uh, so the first part in every ground station is the antenna, which is very much a unique thing for all of us, because all of us may have different objectives to develop our ground station. um, we sometimes develop our ground station for CubeSats. We develop for geostationary satellites. We develop for bigger satellites, or we may develop for rather aeroplane tracking, or APRS, which is the aeroplane tracking systems. So everything, even weather balloon tracking systems, need a ground station basically. So each of this particular utility of it basically needs a different antenna structure as such, since the frequency changes. So based on the frequencies, we have different antennas, and with different advantages as well as disadvantages. On the left side you can see this particular antenna. We call it basically the turnstile antenna, right? So basically the turnstile antenna can be called as two dipoles connected together. um, so we have this two dipoles basically connected, where you can see in the lower pic, where we have two dipoles connected. It is a basic antenna outline, and the length of the dipole basically is the same as the equation of a dipole, which is the quarter wave of I mean the quarter of a wavelength for receiving. So this is our turnstile antenna. Basically, the ground station which I have developed out here at Bharuch has this particular style of antenna, because I majorly focus on the weather satellites as well as CubeSats, basically in VHF and UHF range. So VHF is very high frequency and UHF is ultra high frequency. I will explain the range of frequencies basically later on. But yeah, so this particular antenna is the turnstile antenna, very widely used. Almost a majority of amateur radio enthusiasts has this particular type of antenna. In the above one, we have a simple dipole antenna. You can see it has two poles, and it has an equation of quarter of the wavelength. So it's the most simple type of antenna and very easy to manufacture as well. It's also popular among the amateur radio astronomers. We have here the Yagiuda antenna. Yagiuda is quite famous. You all may have heard about it, and it has a reflector at the back, and in the front it has all the directors, and we have one feed line, which is a folded dipole. So this and this are Yagiuda antenna diagrams, which you can relate with any Yagiuda that you might have seen. And the lengths basically are subjective to frequencies. So you have to calculate the lengths. There are calculators all around. You can Google it. You can search it in books as well. And also you have uh, you know we have various programs for simulation basically. So you can simulate the antennas. Dipole simulation of a dipole is very easy. You get it in almost all the simulation software, and it's quite easy to do. So you can have those tweakings being done, and you can record or view the changes basically. So majority of us, when we start with these type of antennas, which are quite easy to make and easy to use basically. Now I would like to have you all known the fact that um, this turnstile antenna is omnidirectional generally. So you don't have to direct it at the satellite, but its gain is a bit less. But at the same time, we have this Yagi antenna, which is a directive antenna, since it has many directors, and definitely it has very high gain. So, according to your satellite choices, if the satellite emits a very low signal or a very low power signal as such, then we will need a Yagi antenna to get the signals. And if we have a satellite which emits high signals, so high power signals basically, so we can have this particular arrangements too to receive it. So also dipole is also omnidirectional. We don't point it towards the antenna majority. In the majority times we can have some tweaks and we can point it, but yeah, so it's quite omnidirectional. I also have a simulation of it. I will show it to you later on, so you will have a view that how omnidirectional it is. So these are few amateur antennas for different purposes, different satellites, different frequencies as such. Um, Majority people use these types of antennas for VHF and UHF range, which is around 145 megahertz and 435 megahertz. So around these two frequencies, they have this particular antennas being used, and they are quite effective in that particular range as such. So yeah, and majority of the satellite of the amateur satellites, basically the CubeSats, the WeatherSats, which are available to amateur astronomers or amateur radio enthusiasts or amateur ground stations or even university ground stations. So they generally operate in this particular frequencies because they aren't commercialized frequencies. So these are the part um, of amateur antennas. Then we move on to quite professional antennas out here. Now, this particular slide consists of three specific antennas. There is the dish antenna. This particular antenna is basically the Wi-Fi antenna, which we say, which is 2.4 gigahertz antenna, which we say. So it has multiple purposes. It can even have signals of around 1.7 gigahertz, 1.6 gigahertz of frequencies. So it can be used for multiple things. Generally, people use it for geostationary satellites. So weather satellites like GOES, GOES, which is the GOES satellite, which is a geostationary satellite in the west. Whereas we have GeoComSat, which is which is a Korea-based satellite in the east. We have Electro L2, which is a Russia-based satellite. These are all geostationary satellites. Basically, you can search it on net. So such type of Wi-Fi antennas can be used, can be tweaked and used, or can be used for geostationary satellites also. And definitely you can use it for Wi-Fi. So yeah, so it's a kind of radio amateur astronomer kind of a thing that you have to utilize commercial objects or commercial antennas basically for our use, because we can make um, um, uh, a personalized or customized antenna basically in the dish antenna part, but it's quite difficult to make. So you always search for readily available parts for antennas in the amateur range. Quite different in the professional. In professional, you can make an antenna. So here is the log periodic antenna. This is rarely used by amateurs. Generally, very professional people out here generally use it, and it has quite a big range and quite a good directivity also. Yeah, so it's quite amazing antenna which we have come across, and it's a log periodic antenna. And this one out here in the green scenario, it is basically a group of horn antennas. So horn antenna, basically they have a horn at the back, basically a probe at the back, which receives the signal, basically, and these are the reflectors around it. Horn antenna majorly, or it's many times used in 1420, which is a radio astronomy frequency. 1420 is a very celebrated frequency, I guess, or a very well-known, famous one. It is the H1 line frequency, basically, where basically uh, the H1 line absorption as well as the emission part, the H1 line emission, basically happens in this particular frequency. And we generally use horn antennas as well as dish antennas for receiving such type of frequencies as such in radio astronomy. So it's many times used in radio astronomy. This dish antenna, Wi-Fi type dish antenna, also has some range in 1420 part, but definitely we will need a bit tweaking in the Wi-Fi antennas to receive 1420 part, like we have to increase the reflector part, the dish part, a bit, by connecting it to something. And majorly this is a issue where we have to increase that particular part, and we have to tweak the feed part also, the feed part basically of the antenna. So definitely, but this can be easily used for 1420 also, the Wi-Fi antenna. It has been used, and I have seen people using it. So um, yeah, so this here we end the antenna part, where we are clear that how amateur antennas look. Generally they are omni directional antennas, so you don't have to point it to a particular satellite as such. Um, and some are directional for satellites which are not transmitting that high level or high power signals. So here comes the we come to end on the antenna part. The next important part in a ground station, basically after antenna, is the amplifiers and filters, basically. So this may or may not be required, right? So those antennas which have lower gains may require this particular amplifiers and filters, so that they can receive those satellites which don't transmit well, or don't transmit high power signals. But many times for weather satellites, also amateur weather satellites, and almost all the CubeSats, basically, we don't need amplifiers and filters generally. But yeah, if you are at a place where you have high interference of the surrounding signals, so it depends upon where you are, what's the noise around you. You have to do your noise calculations. If your noise bed is higher than the signals, then you won't receive the signals. Yeah, so you will need amplifiers and filters to filter that particular thing. And definitely in radio astronomy you need it, because radio astronomy signals are very very minute and very delicate, and you will need multiple filters as well as amplifiers for radio astronomy part. But for the satellite ground station part, you may not need, for some satellites which transmit on a very high power level. So as you know, the amplifiers amplify the signal, basically our signal, and the band pass and band stop filters, basically they pass or stop a particular band, right? So which is FC1, between FC1 and F2 it's passing, and other it's isn't passing. This is the threshold limit, and here this is the threshold limit, except this particular band FC1 to F2 it's passing. So this is the basic graph of a band pass filter. And this particular picture down here is sawbird plus nova. It's a mixture of amplifier and a filter for nova satellites. So you may not need it, because these particular sawbird plus nova is recommended to those who are in cities and who have lots and lots of interference around. So you will need amplifiers as well as filters for if you are using omni directional antennas, which aren't pointing towards the satellite to receive the signals. So here we know that how and why we use amplifiers and filters. They may or may not be necessary. In my ground station at Bharuch, out there, I don't have any filters or amplifiers, but still I receive a good quality signal, right? So I have done my noise calculations out here. It's very quiet out here. I mean, there are no radio noises out here, so very less radio noises out there. So definitely, I don't require amplifiers and filters in my ground station till now. If I need sensitive reception as well as radio astronomy, I will definitely need one of these to have, right? So yeah. Then we have our next part, which is the receiver setups. So this is the traditional receiver setup which we have. We tune in the frequencies by turning the knobs, and we receive the signals around, and we have our gain controls, we have our phase controls, we have our all the scannings, etc. out here. We have our dial pad for the frequency setup, etc. And we have this particular traditional setup of our you know receiver devices, where the signals are actually received in that particular range, basically. But at the same time, we have this particular small USB type gadget, which we call it as SDR, which is software defined radio receiver. So what is the software defined radio receiver? So in very layman terms, a software defined radio receiver is basically um, a digital converter of signals. So whatever signals it gets, it's converted into a digital format which can be read by a software, a particularly designed software which can read this particular signals, digital signals basically of SDRs. And then that particular software receives the signal through the port, basically the USB port, and we can operate through it. So since the signals become digital, the losses are less, and that's why we always recommend that this particular part should have a longer USB cable and a shorter a coax cable. Basically, we recommend this generally. So this particular tweaks also helps in reducing the noises around, which can enter through your coax cable, because not many coax cables are lossless. I mean, no coax cables are lossless. Every coax cable has a attenuation ratio. Attenuation means they decrease the signal with the length, and definitely so coax cable should be less. Yeah, no doubt. We also lose digital signals also through the USB part, but it's very less, and the attenuation is so less that it's negligible. So definitely we have this particular practice where we keep the USB part or the USB cable to the computer a bit longer, and the coax cable a bit shorter for this particular SDRs. But for this particular setup, you definitely need a coax cable. So it's a traditional setup as such, and yeah, so this particular setup is a bit better as compared to this particular setup. They give a higher range, they give a higher a better output as such, but they are quite costly also, and they are a bit tedious to assemble and operate as such, because then you have to connect it and you have to sync it. You have to sync the frequency settings, you have to sync the frequencies and then receive. Whereas this particular SDR can be automated, because at the end your digital signals are then getting into a software, and a software can be automated or easily clubbed with other software. So the decoding software can be clubbed with this, and our Orbitron or our satellite tracking softwares can be clubbed into this easily, and we can have a automated type of setup which I have in my ground station, where we receive the signals automatically. I mean, as soon as the satellite comes in my range or my ground station range, it comes above the horizon, its elevation increases. Then subsequently, my tracking software detects it. Uh, they have a formula in it, and they detect that yeah, the satellite is in the range, and now we should switch on our receiver software, and they switch on the receiver software. The receiver software then detects that yeah, you have this particular satellite in range, and I should now switch on my decoding software, and then they switch on automatically the decoding software, and the whole process goes in a sync. And you don't need to set up your frequencies, then switch on your decoding softwares and then decode it, and those type of tedious works are not required as such in SDR. So it's quite a good gadget which have been in the field, in the market, and definitely I use RTL SDR. Basically, you can use any type of SDR depending upon the frequency range. So each SDR has their separate frequency ranges. RTL SDR works good for weather satellites, UHF, VHF, and as well as geostationary satellites. Also, it works good in the L band. Basically, above L band, it doesn't have any reception as such. But yeah, so this is basically your SDRs. You can also add various other gadgets so that your frequency comes in the range. Basically, like we have ham it ups, we have LNB. Basically, LNB is low noise block, which we have in our TV antennas, which actually reduces or converts the frequencies into lower frequencies from KU band. Basically, they convert it to the lower frequencies. I will tell you about this L bands, KU bands, VHF, UHF in quite some time. You will definitely get that information. Don't worry about it. So these are the receivers which we have. Then this is the specific decoding software which we have for our SDR, for my SDR basically. So yeah, I will have a show of live decoding from my recording. Basically, I have recorded the SSTV from ISS. So this particular SSTV, which is slow scan television signals, which we get from International Space Station. Basically, it's quite rare. Only on occasions they send. And I was lucky enough that after newly starting our ground station out here in Bharuch, I was lucky enough to get one such occasions in August, which is the 3rd, 4th, 5th of August, 4th and 5th of August, basically. And I was lucky enough to receive a few 4 images from this slow scan TV from ISS directly. So this is the frequency on 145.800 megahertz, and yeah. So we have it in FM modulation, which is the frequency modul wide band frequency modulation type, and this is the bandwidth. This is the order. Basically, bandwidth is 34 kilohertz, around somewhat around 34 kilohertz. You can see the signals out here, and we you can switch on FM stereo or not. It depends upon you. At the end, you are directly transmitting the signals to this particular decoding software out here, which decodes the SSTV signals around, and various modes which the decoding software has. So it's specialized in its operation. And this is the audio part where you define the latency, where you define outputs and inputs and all. So this cable output is directly the input of this particular decoding software. So this particular SDR software basically receives the signals from digital signals from SDR, relays it in the form of waterfall format. This is a type of waterfall where you can see the fall, and below it there is a waterfall. I will show it to you. So this is also a type of waterfall format out here. Then through this we relay it to our decoding software. As I said, our switch on itself, and then it relays it directly to our decoding software, which also switches on itself. this is the automation we have. But since I will be sharing, or I will be showing you it may I won't be relaying the automation as such, right? So yeah, frequency band which I was talking about. Yeah, so after this particular slide, I will be showing you demonstration of how we receive the SSTV from. I have the recording, and we will see that how SSTV is received from our. So before that, this particular slide is very important for radio astronomers, for uh, ground stations which are amateur also, and because this particular this frequency actually tells us uh, the basically of different sections of frequencies. So we have maritime navigation signals which is very frequency, right? Here we have VLF range from 10 hertz to 1 kilohertz as such, very low. Very big antenna is used for this. Frequency is very low. Very big antenna. Basically, maritime navigation generally is done by this particular part. Then we have the low frequency band. Also, the navigation aids are given. So these are terrestrial navigations. Basically, they may not be satellite based. They are generally terrestrial all from VLF and LF range. Then we have AM maritime radio, which is in MF, which is middle frequency basically. Here you can have the ranges basically of it, 100 kilohertz to 1 megahertz. And by the way, our SDRs basically can receive. I have seen SDRs which can receive up to 1 kilohertz, and my SDR receives up to 500 kilohertz of frequencies as such. 500 kilohertz of frequencies, and the below part we cannot receive as such. And SDRs which are good enough for amateur radio amateurs basically, or I guess the amateur ground stations, they may receive up to 1 kilohertz. Below that, we will need at the same time we will need an SDR which receives below it. So it's kind of difficult as such, but definitely some part of VLF range and LF range, MF range, HF range can be received. This which I was talking about, this VHF UHF range basically. So here we have this VHF and UHF range, which is also yeah. So VHF TVs are not everywhere. They are quite restricted. We have FM radios, which we have this 92.3 all, which has this in VHF range. We have navigation aids, and we have which are the NOAA satellites, which have around 137, 136, 137, between 136, 137 megahertz, and we
Hello.
have our yeah. So anyone has wanna ask something? Anyone wanna ask something? So they had this. Yeah. So let me finish this particular slide, and definitely we will answer the this particular part of questions now, because there are pretty questionnaire around out there. Uh, so everybody because it will be very useful for you. You can have a screenshot of this particular slide also. S C X K U K K A, which I have used VHF, UHF, SHF. So like when you enter this particular world, nobody will tell you that, yeah, so it's between let's say it's between 1 to 2 gigahertz. No, they will say it's L band. So yeah, definitely you should take a screenshot of it, I guess. So let's address the you know our questions. Uh, yeah, so Manila, are you able to see the screen now? Because I guess everybody of us are able to see the screen. Uh, yeah, Arpit Verma says, can I successfully track a satellite using WebSDR? Those satellites are not seen from India. You need to go to the West world for it. So to America, basically, if you are in America, definitely you can track with or yeah. So you have said WebSDR. So yeah, it's WebSDR which is written. It's WebSDR, I guess. So yeah, WebSDR you may be able to track, but the results are not that good. I have tried with WebSDR. Many have tried, but yeah, no. You may not get good signals out there. So no, you have to have your own SDRs for Go satellite, I guess. Uh, Club Cosmos. Okay. Yeah, Rachel, I would like to illustrate web SDR basically is a web-based SDR. So you can get the signals from it, but the signals are not that good. And since you cannot, relay, like if you see the signals which we get from SDR, so it's like for 1-2 minutes you get 2 GB, 3 GB, 4 GB of signals, or signals are relayed. And I guess you may not have that particular high internet connections out there where you can receive that particular high, or they may not able to relay that particular high signal. So definitely, yeah, Ghost satellite is a no-no. It's a geostationary weather satellite, Ghost satellite. Uh, okay. Uh, can we transfer or send any messages to? Definitely we can. But for that, you will need, for transfer of messages, you will need your call signs, and you will need the license as such. Then only you can transmit in your frequency range, basically, which you have been allotted, or and you have to take care of that, take care of legal formalities. But definitely you can have transfer or send any messages. Definitely, I have received Arabic messages, basically, too. uh, actually, so I will be showing it to you shortly. I've received it, I haven't transmitted it, so that's receiving is allowed. um, Signals of yeah, so ISS, actually there is a website, you can google it. ISS tells it, which I guess ARISS it is, which is amateur radio thing of ISS, where you can check. Thank you. Good reference book for radio astronomy. I guess you should start with H1 line 1420 hertz. Try to search about it, right? Then we have Shrikant Deti, which is up to what extent can I use this method to track celestial bodies uh, not only coming towards Earth? So it depends upon your antennas, basically, that up to what extent you can capture. But those celestial bodies which emit a particular type of electromagnetic radiation, so definitely through the Doppler shift you can have a track that if they are coming towards Earth or they are going away from Earth. As such, you can even map the galaxy. You can even have the dark matter theories parts being verified or being calculated as such. uh, Majorly. Yeah, there is a lot of question out here. uh, can we use
Uh,
this antenna for signal systems? And yeah, yeah, Rital, you were saying anything?
no, I think what you can do is you can just complete with your presentation so that you don't
Okay.
break up your link, and then we will switch on
Yeah,
to all the questions.
yeah. So let me show them something. The SDR part, the decoding part of ISS signals basically. I guess I've answered all the questions, I guess. So, okay.
Yeah, you can show your results, the photos that you've got, especially the ISS picture is so beautiful. You can share that.
Let me show them how I have received it. Uh, 1 second. I will share my screen. 1 second.
Uh, till he shares his screen, I'd like to add one more thing that he said. You can receive the images from ISS, and if so, one of you have asked that can we use this antenna to transmit? So yes, we can use this antenna for transmission, but for that, as Ankit said, you need to have a license. So to be specific, we need to give appear for a ham radio license, which has two parts, VU23 and VU3 exams. So I'm currently appearing for VU2 exam, wherein I can just receive the call signs from other ham amateur radio stations or from the ISS. If I want to transmit something, or if I want to talk to astronauts on board International Space Station, I need to have my own call sign. For that, you have to appear for VU3 exams, and those keep appearing. Those exams take place throughout the year, but you just have to check for the opportunities or check for the exam centers. If anyone is interested in going for those exams, please contact me. I'll leave my phone number here. You can contact me later. Thank you.
Yeah. So, are you guys able to see now?
Yes.
Yeah, yeah, the screen is visible, right? So we have these two softwares, which is the SDR software. First, I will show you the waterfall. This particular part is called as the waterfall of the signal. So here we see basically how the signals are, and definitely you can, if you have an unknown signal with you, you can take a click of it and you can share it on Facebook and say that, yeah, I'm getting this particular waterfall, what it is. You also have a wiki page of it where they have different type of waterfalls and the sounds of it, and they have classified into from where the sources are. So let us start with, I've already loaded the file. Let us start with this. Okay, I will search it. And so this was the signal from International Space Station. It will appear it now. It's a recorded file, and you will see that how amazingly this particular software will decode it as such. So here it comes, and it detects it, and it starts receiving um, line by line. Yeah. So have this beautiful view of how we have decoded the International Space Station SSTV, slow scan television as such. And yeah, so this particular, anyone knows Russian out here can definitely you know, have that particular Russian text being given. Yeah, so I want you guys to notice this particular signals. This signal will show a Doppler effect. It will start from lower frequencies and then it will go into higher frequencies basically. So it's a very amazing view that we can even verify Doppler effects out there. And see, in my pictures also you can see this particular Doppler effect being coming, right? So as the frequency, as the satellite elevation increases, the satellite is nearer to us. This the particular Doppler effect happens, and since the satellite is moving, so we have the reception. The transmission is at a different frequency. The reception is at a different frequency. So this particular Doppler effect can be seen out here. You can definitely see it out here, and this can lead to some distortions in images. Basically, we can correct it later on. Don't worry about it, and just enjoy the decoding of the signals from our international space station. So it's Intermay 75, which is the translation of this particular Russian text. Is August 2020, and that's it. It's our first signal, and the second signal will come after 3 minutes because they have a 3 minute gap between two successful transmissions. I will, in the meantime, show you the history. Okay, I have this particular history. Uh, yeah, yeah. So this was given to us. This was the actual picture reception. I have corrected the Doppler shift out here. Uh, and this particular picture is the most amazing pictures. This is a picture, and these are the four pictures actually which we have from international station which I have received. 1, 2, 3, and 4. So we have an amazing reception. One more reception is yet to be received now. It's like it takes around 3 minutes of a time between, as I said, between two particular successful transmission, and it's also a recorded form, obviously. It happened in 4th of August, around in the evening, in the night, basically around 9. It actually transmitted. It went over us, and it actually had this particular transmissions being done. You can see this, but here you can see the signal level. Basically, here you see the noise level. This is the waterfall we have. Here also we have this particular waterfall where we cannot see any signals around. Out here we have the mapper basically, and here we have our main panel where we see that the signal is coming or not. We have minus 40 dB of our noise, where I have set all the gain parameters and all the noise parameters as such according to my location as such. And we have this frequency modulation, wide frequency modulation out here. These are different modulations where we select the one which we need, which is a narrow frequency modulation, amplitude modulation. Here comes, and now you see the frequency is totally different. uh, it has started decoding, and here you see the frequency is bit off. It's a Doppler shift. The satellite is going um, lower. The elevation is going lower, and the satellite is going away from us. So we have this particular Doppler shift around. And this is our second decoding, second picture decoding out here. I was explaining you the different modulations: amplitude modulation, DSB, which is double sideband, lower sideband, upper sideband, continuous wave, and raw signal. So these are the modulations which we have. We have it in our radios also, similar type of modulation. See how the Doppler shift is. It has totally shifted the frequencies, and this particular thing is a bit clearer. So yeah, the Doppler shift isn't distorting the image a bit. So we have this particular person out here, some officials from Russia. So here we again have some distortions from the Doppler shifts as such. It will be corrected, no worries about it. We can correct it later on. So it's the slow scan TV of International Space Station as such.
Ankit, could you please tell how do you track International Space Station and how do you know when the
Yeah,
ISS is
I am
transmitting the
coming to it.
signal?
I am coming to it. We use a software which we call it as Orbitron, right? So I have that particular software. I will be sharing it once. That's quite a bit, which after this particular workshop. Yeah. So that's all. This is the second, and here we are done. This is all. The two we get in 10 minutes time frame of International Space Station when it passes above us. So that's it. Uh, Let me share you Orbitron. Give me a minute. Yeah, just give me a minute. I'm just opening the software. Search. So this is Orbitron. 1 second. So let me share the screen now, you all, so that you all see. Share it. Share it. Are you able to see the Orbitron? So this
Yeah.
is the basic interface of Orbitron, right? So we have this real time and we have this simulation time, right? We have different type of satellites out here. These are weather satellites basically. We can load the TLEs, weather satellites, visual stations basically. So I have set the stations now. And we have this ISS out here. So this is the ISS. This is how we decode the ISS. This is real time and simulation. We can see basically when the ISS, we can actually simulate the ISS pass over Bharuch. So we can have it. Plus we can have the prediction setup out here. So let me get back to real time. Here the prediction setup we go. We have selected all the predictions and then we predict. So this is the time when we will have the ISS pass out here at Bharuch, which is our ground station location presently. If we click on it, we can see that this particular ISS pass uh, is starts out here, and this is the highest elevation 43.1, and this is the lowest elevation out here, and the timings of it basically. So this is how Orbitron works. Plus we have this radio rotor part where you can launch the decoding Sdr software by just clicking the drivers off, and then the software will be launched like this, like you see here. I have launched my software out here, right? And at the same time it is totally bounded to the frequencies now, and it will track the frequencies as I started. So it will track the frequencies as such, like, yeah. So overall now it won't be tracking because it's in the recording mode. I mean playing the recorded file, but it does track the frequency out here. So here is how we compensate the Doppler shift basically. So you can see out here, if I play from in real time, you can see the receiver Doppler out here. You guys can see, right? Receiver slash Doppler. So this is the Doppler corrected frequency where you will be getting your signal, not this. So here you see that what Doppler shift is and how Doppler shift is. So you have to receive at this particular frequencies to receive signal from ISS, not this. This is the frequencies which we have kept, which is the original ISS frequency. So overall, this is the overall Orbitron setup out here. We have different type of uh, satellites out here where you can select around XCOM with weather satellite. You have the NOAA satellites out here. GOES. See, GOES are geostationary satellites, right? GOES 13 no longer transmits. We have GOES 14, GOES 15, GOES 16, GOES 17, right? So these are not, covering India. So you have to have somewhere your SDR around in USA for the GOES satellites. We have Himawari satellites, which are also weather satellites around. We have this NOAA, the very famous NOAA satellites. So 15, 18, and 19 are working, and definitely we have received from 15, 18, and 19. So yeah, so these are the NOAA satellites around. Meteor M2 is also working satellite. Meteor M2 also we can receive, and Meteor M2 is very, very amazing satellite because it is very highly accurate. It can even tell you the location of a pond or a lake nearby, which is obviously quite big, but definitely it will show you. I will show you the pictures from Meteor M2 which I have got. They are astounding. So here we end our basic demonstrations of softwares as such. Yeah, so I also wish to show you my you know, a simulation, a short simulation of dipole software. I mean, in a software, in a simulation software, a very basic simulation software. So let me have that software set up. One second. Yeah, so let's have a view of it. So this is the MANAGL, which is quite a good software for amateur, uh, antenna designing and all. So this is a dipole setup where we have two dipoles, and this is the reflector down. So it's shorted, reflector is shorted, whereas the dipole has a feed in between. So we calculated for 137.1, which is our meteor as well as nova frequency. Meteor Meteor M2 and Nova 19 frequency. So since we have calculated, we can have this far field plot, which you can see is omnipresent from north to south, but not east to west. We can see the 3D part. See, you can see it's receiving from all directions, from north to south, definitely. And since these Nova 19 and Meteor satellites are polar-based satellites, they fly from north to south and south to north, which is the northbound and southbound. And definitely, so you can see it's you know, uh, omnidirectional as such. The reception, it's horizontally polarized and omnidirectional. Uh, it's horizontally polarized. Its height is 5 meters, which I have kept, and it's quite a good software for analyzing. You should go through it just to indicate the stuffs. So yeah, majorly this is part, and now further, Rachel, I should have a showing of our basic report, basically, I guess.
Yeah, you can show them the pictures that you have got using the from the NOAA satellites. Uh, I mean, I want you to share those pictures. Those are beautiful images. And
Yeah, let me
while
share the
you,
top ones, right? The ones which are internationally accredited also.
yeah. So I think because we are also at the end of our time, so
Wow.
while you share your screen, I'll just like to tell or ask students from MIT College, from MIT WPU, that many colleges are now having their own ground stations. We have at most, at least two ground stations that I know of. One is in College of Engineering, Pune, and other is in IIT Bombay. As these people are also having their student satellites up there in orbit in this space. So we can, and making a ground station doesn't take much technical knowledge or much efforts as well. By just simple learning things, you can make your own ground station at home, and we are trying making an attempt to make one for our college as well. Let's see how it goes. Anyone interested in this project, please do let us know. You can also join these efforts and have our own ground station.
Yeah, so this is our library as such, where we have our images as such. So let's start with 23. So this is a composite image of Meteor M2. 3 days composite image. You can see the timings out here. But let me show you the real thing. Right. Let me zoom it to a very high level. You can see the snow, right? If any one of you can
Yeah.
switch on your mic
Yeah,
and
yeah,
you
of
can see
course.
the smoke, the snow. Basically, you can see the you know lakes, rivers. You can see river. You can see the Sindhu River, the Indus River out here. You can see peaks, basically the snow, basically. So this is the accuracy of Meteor M2. This is a Meteor M2 image, and with its all, you can have this particular part, and this particular. So this is how beautiful the image can be from Meteor M2, the whole overall India image, basically. Um, on
And
the
guys,
content,
let me tell you, this is not something he has taken from internet. These are the images which he has received himself
received.
using his own ground station.
Yeah, so these are the images which we have received from our own ground station, our very own ground station at Bharuch. Uh, so let me show you the Noah images also. Uh, these are India 2 images. Let me show you the first of where is it? Where is it? Uh, 1st of June. What happened at the 3rd of June? At the 3rd of June, we faced very uh, cyclone Nisarga. So here is the NOAA image of Nisarga cyclone. You can see clearly out here the Nisarga cyclone being born. It's the 1st of June, where we have received from Bharuch as such, and you can see this particular Nisarga cyclone out here. You can see the precipitations building. Uh, so these are few things uh, out here of the Nisarga cyclone, the base image of it. So these are the NOAA pictures. At that particular time, we weren't capable enough to decode the Meteor M2 picture. So this is the NOAA picture of our cyclone Nisarga, which have come at 3rd of June, basically. So we have this. Uh, we have many pictures around, many pictures around. This is a composition of whole of India around India. So India composition. So this particular picture which you are seeing out here, this is being published internationally, and we have given accreditations for it. Let me show you the publication where it has published. Let me show you guys. My actually tab got crashed, and I had.
So up till you share your screen, I'll just also like to add one more thing. There was a question about how far we can see through the radio telescopes. So the plus point of using the radio telescopes is you can see objects that are very far away beyond the reach of the optical telescopes. So because radio waves are something that can travel even through a very dense dust of clouds. Say for example, there are nebulae, there are many dust things around the solar system and all. Still these radio waves are able to pass through it. And there's a one huge radio telescope in Maharashtra, the giant microwave radio telescopes, and I will like you guys to visit the GMRT. It's a very beautiful telescope, not just a single telescopes. Those are, I guess, some 30 telescopes. And recently, the father of our radio astronomy for India, Dr. Govind Swarup, he recently passed away, who led the foundation of these radio telescopes.
Yeah. So
Okay.
yeah, Rachel. So let me have this particular achievement of ours being noted by others. Uh, we had collaborated with people. I mean, they had collaborated with us actually. So we lended our hand basically for people who are at London as such. There was a event at London as such. They call it as the Nowcast event, and where they asked images from all over the world. As such, we have provided these two images. We are very glad that our two images are selected as such. So these two images are given the Indian subcontinent as such, are given by us, and definitely our name being mentioned in the about section. As such, I will zoom and I will show. Here we have Ankit Sharma, which is my name. As such, bring that particular image via our ground station. This is the zoomed out image of it, and we see various countries around and our beautiful India around out here above. The weather around, as such, it was quite clear in Bharuch. Yeah. So overall, we had this particular achievements our ground station had at the international level also. So station which we had got recently for our ground station. I would like to share the Urdu, I mean not the Urdu, the Arabic text which we have received from satellites. So these are amateur satellites which they have built. What they have done is they have had transmog in it and few satellites like satellites and the nave one satellite basically are the satellites which transmits few messages regularly as they pass on above us. So, let me share. So let me show you. So this is our ground station report where we have given all the space as such, and 3D images also we have received. We will relate also classes, but the red and green classes, red and cyan as such. So these are the images which we have. These are the CubeSats which we have set parameters basically, which you have received from Cube one. This is the airplane the Blue Dart Aviation and all received from us. So we have received over aspects now, and here you can see the satellite above. We rarely. This is when I went at home and I had received this particular satellite when our ground satellite portable. I did establish it elsewhere. Now it's quite big. Uh, this is a CubeSat satellite. Yeah. So this was the Arabic message which we get. First non-English message which we got, which is the Arabic message. So this is the particular Arabic message which we got, where it translates as this is translated by. So don't blame me if the translation is quite off. So these are the second pass, and this is the total pass, 100% pass translates. It has a beautiful poem which I would like to share. The poem for the sheriff. What's with the hostel? The long nave. Nave can be named literal meaning. This was translated by a person. The poem is Barak Russell Sharif.
If you can
So this is
share the
basically
poem, if you can share the poem, I will read it.
Okay, yeah. So, right.
Picture quality is low.
Okay.
Uh, I think what we will do is we will share this report with everyone who is interested.
We will worries about it. We will share this report. Don't worry that you may not get this message. We will share. You can even ask us. I will give you the real picture also of it.
Yeah. So whoever
Yeah.
is
So
interested,
let me share the translation also. The poem is Barak Russell Sharif. What we have come down with. Here the long fine is mine and the view is beautiful. This is the poem base.
भाई आप एक बार आपका व्हाट्सएप मैसेज देखो.
Yeah. So this is the transmitted by a NAIF 1 satellite. You all can also receive it, and it's quite interesting to receive a non-English message, basically. Yeah, Rachel, so over to you, basically.
Yeah, so guys, you must have seen that Ankit has worked on this quite a lot, and we have so many things to share with you. But due to time constraints, we have to cut short many of the things, many of the good details, finer details. But if you are interested, please contact Ankit. I will ask Ankit to share his number as well as email address, whatever he is free to share. And you can later contact him and ask him. We will also upload all the PPT and the software related information on the Telegram group. So guys, also please join the Telegram group and let others also know about this. Also, you can be a part of this ongoing project, Project Ground Station, which is actually done by our college itself, our college students. Another Karna ma'am is helping us a lot in submitting this project proposal to the authorities in our college. And because of her efforts, I think we will soon be getting our own station or a place where we can set up this thing. Uh, and again, we will have a special session on Radio Astronomy itself. Today, we heard about ground station. Soon, we will also learn how to use the radio telescopes. Last time, Rohan also gave a gist about it, how you can use the robotic telescopes. Okay, then let's meet next week with another interesting presentation. I think we will be having a presentation on CanSats, that is the satellites in the shape of a can, which is another project that is done by our college students itself. So stay tuned and stay safe. Okay, and anybody if, has any question, you can just unmute yourself and ask, or can ask later on the Telegram group. Is there any
Okay, so yeah, I would like to say something. My internet connection is not that strong, so in case you have trouble hearing me, it will be network issues. So am I audible now? Like,
Yeah, ma'am.
okay. So I would like to say that Ankit has put a lot of efforts in building this ground station, and I really appreciate being from mechanical engineering background. Not only Ankit but other students also who are from mechanical engineering background. They are coming up with the projects which require expertise from different fields of engineering. Okay, so that way I would say that anybody from here, from students who think that they are not well equipped to understand the technicalities, so all these students have not actually been guided by any expert in this field, and they have the basics of this field, they have developed their understanding on their own. So it is very much doable. And I appreciate Ankit, well done. Your presentation was really nice and informative. And I just have one question to ask here. So you said for the amplifiers and filters are required if we want to really do the noise cancellation. And you said you have kept this setup in Bharuch where the noise levels are low, radio noise levels are low. So you are not using this filters as such for the noise cancellation. Right? Am I right, Ankit?
Yeah, ma'am. Yeah, ma'am. Our particular ground station doesn't have it because it is quite a lot of investment as such, as well as the assembly structure is quite. In my scenario, basically, the assembly structure is quite difficult as such in Bharuch. So that's why I have tried to avoid it as far as possible by using other tweaks majorly.
Okay, but then the kind of reception that you have got I mean, you could get it with no noise at all, or like what was the experience when while receiving the signals?
Yeah. So as soon as the satellite, starts from the horizon, till around 20 degrees, you cannot receive it. If you want to receive that particular part, then you will need amplifier and filter. After 20 degrees to 20 degrees, you can receive it. And definitely they are quite good depending upon satellite to satellite. Right. Those satellites which don't transmit well or which transmit at a very low power wattage, etc. So they have quite issues with it. You get the reception sometimes when they are very above yourself or they are in your range of antenna, and then they disappear. So this my I do have lots of noises in my pictures. Actually, you can also see it in my receptions also. So yeah, I get noises out here. It's not noiseless, but I get good receptions out here because it's a bit in a not in the city part. I guess Bharuch is basically a village, a kind of a now developed into a city. So there is not much noise as such out here.
Okay, and one of the images that I saw that we received from ISS, that certain letters I've seen that are appearing as a mirror image. So my question was, is it a kind of a problem due to noise around, or is it the problem in the decoding of the message?
I guess that was Russian, I guess. The decoding was Russian, but definitely there are no mirror images in it. And the images which I shared later on, they are quite clear, I guess. So they might be Russian in language. So the Russians has that particular type of fonts.
Oh, okay. All right. Okay. And if we want to set up this, we want to have ground station in our campus. So for that, we have to. I mean, how are we going to do the noise calculation there? Like, it's going to depend completely on the environment around, and like what kind of parameters we need to consider while selecting or proposing any amplifier or filters to use.
Yeah, so our ground station specifically would be a bit multi-purpose, which I basically have proposed. So in that particular part, since Pune is a city, I had selected low noise or low losses cables, which is RG216, which I have selected. How I did the calculation was I basically checked the how much what people are experiencing in Pune. So I had many people around. I had a chat that what's your noise levels and around etc. What's your basic noise bed level basically what they experience. And upon that, I had a few parameters selected that my signal should be this high, and my coax will be this long. So every coax has an attenuation value. Like this RG216 has attenuation value of around 5.5. Means upon around 10 feet, around 15 feet, you have this 5.5 dB of downfall.
Okay.
So accordingly, you can get it on the net. So accordingly, you calculate that your signal from basic satellites basically should be above your noise bed basically.
Okay.
So the noise bed out there is -30, around -30, I guess. I have to check with them. But yeah, this is how you do the calculations as such. And if you are so there the gain of antenna also matters. If you have a high gain antenna, then you may not need this particular amplifiers as such. But since our antennas, which we have designed, have a wide range of frequencies and they are omni directional, so they have a quite a lower gain. So definitely we might need amplifiers and filters sometimes. Filters are basically location specific. Amplifiers may be a bit bigger location specific. In cities, we generally need amplifiers.
Okay. And
Antennas, ma'am. because we need
Okay.
different frequency ranges. Since I said it's a
Okay.
multi-purpose antenna, so
Mm-hmm.
we are designing around 5 antennas which we'll be working with. Out of
Okay.
which three of them will be omnidirectional and one of them will be directional, and I guess two of them will be one for our geostationary satellites and
Mm-hmm.
one for our radio astronomy purposes.
Okay. Okay. Fine. So same setup can be used for all these multiple
Yeah, you,
antenna.
you just have to change the antennas for different frequency receptions, basically,
Okay,
nothing else.
but my query is considering the different designs involved and their like as you said the gains are different. Accordingly, certain parameters will be changing. So, I mean, do you expect any kind of noise
Yeah,
entering?
yeah. So since we have an amplifier in range, so
Okay,
the gain generally doesn't matter much. Even if we have a low gain, we are at if we have a high gain, we are at an advantage. If we have a low gain, we are still getting the signals.
okay,
So
okay.
we have an amplifier already set in line.
Mm-hmm.
And this second thing about it is that these different antennas are for different frequency ranges, so they
Okay.
all work differently
Mm-hmm.
altogether. So there may not be any issue with all the
Okay.
antenna syncing. Plus, we have a design which is in such a way that we can work with all the antennas, and definitely they sync very well with our RTL SDR. They are within the frequency ranges as such.
Okay. Okay. Fine. Okay, thank you, Ankit, for such informative talk. So I'm done. Over to you, Rachel. If you want to
Okay.
conclude.
Yeah, ma'am. So, uh, I just have to say that interested students, please join, please spread this word in our college, because many of the students don't know what is going on, and there are really good projects. These are really good projects, which they can also take as their final year projects. So also tell your friends, guys. And okay, we will be ready with our next presentation next week. So stay tuned. And thank you so much, ma'am. Thank you, Ankit. Yeah.
Thank you, Rizal.
Yeah. Okay, then we will end this meeting.
Yeah.